Unit 1, Lesson 2, Part 2. We are now on example number 4, and we're going to show you the 3 ways that limits can fail to exist. So, case 1, the left-hand limit does not equal the right-hand limit. So, as you can see on this situation right here, it says justify why the limit does not exist at x equals -1 for f of x equals the absolute value of x plus 1 over x plus 1. So we're going to look at the limit as x approaches -1 from the left. And if I'm coming in from the left, I'm coming in this way, I'm approaching my y value of -1. So that is -1. And now we're going to look at the limit as x approaches -1 from the right. And so I'm coming in from the right, my y value is +1. And we're going to say since the limit as x approaches -1 from the left of f of x does not equal the limit as x approaches -1 from the right, f of x, comma, the limit as x approaches -1, this general limit then, equals does not exist. So that is a jump discontinuity. And that limit will always fail to exist at a jump discontinuity. Okay, case number 2. Oscillating behavior. Okay, so justify why the limit does not exist at x equals 0 for f of x equals the sine of 1 over x. So we're going to say by inspection, meaning you put it in your calculator and you see this oscillating type thing right here. So by inspection, look at x equals 0.1. Limit as x approaches 0 from the right, because 0.1 is from the right, and that limit is going to be negative. If you look at that in your calculator, if you put this function right here in your calculator and then look at what the value is at x equals 0.1, you're going to have a negative value less than 0, while at x equals -0.1, limit as x approaches 0 from the left, because if it was negative, it'd be coming in from the left, this is greater than 0. Therefore, the limit does not exist. So sometimes you can't really do anything algebraically with this function. You just have to kind of say, well, I just want to look at it at this value and at this value, you know, one on the left and one on the right, just to see if it's going to the same place. The last one is unbounded behavior. Justify why the limit does not exist at x equals 2 for f of x equals 1 over x minus 2 quantity squared. So for this one, we're going to look at the limit as x approaches 2 from the left of f of x. And if you're coming in from the left, you can see that your y values are going to infinity. And the limit as x approaches 2 from the right of f of x. If I'm coming in from the right, I imagine I put those x values in, I look at what my y is doing. This is also infinity, okay? But by definition, infinity is not a real number. Infinity is the behavior of the function. So even though on both sides it's going to infinity, and really we would say, therefore, the limit as x approaches 2 of f of x is infinity. This is actually talking about the behavior of the function. If the limit exists, it equals some value L. Like for limit, we always say L. If the limit exists, it actually equals a number. So I want you to, tell me if it's doing the same thing on both sides. So since it was going to infinity on both sides, then, this would have been the answer to the limit. But that technically means that the limit does not exist because it's not an actual real number, okay? Which that's something that's one of those difficult things to explain and difficult things for you to grasp. But I will ask that you tell me if it's doing the same thing on both sides, even if it is infinity or negative infinity. But that does not mean that the limit exists. Okay. So now topic 1.4, estimating limit values from tables. So example number 5, now consider the function f of x equals x minus 3 over x squared plus 2x minus 15. Complete the table below to find the limit as x approaches 3. So I suggest that you put this in y1 in your calculator. Okay, so that needs to go in y1 in your calculator. This is a calculator problem, and when you have a situation like this, where, they give you that function, you're going to just look at, once you get it in y1, then you'll go back to your regular screen and you'll do y1 of 2.9, and then it'll give you a value, y1 of 2.99, and it'll give you a value. And remember, to get y1 on the TI-84, if I wanted to get y1, I'm going to hit vars, then I'm going to arrow over to y vars, and then I'm going to hit number 1 for function and number 1 for y1. Okay? So that's how you get it back after you've put this in y1. Then go back, quit back out so that you're on your normal screen, and then calculate your y1 of 2.9, y1 of 2.99. Go ahead and stop and fill in these and come back and we'll see if we have the same thing. Okay, so you should be back and you should have gotten the same thing that I got here. Notice that here we're approaching 3 from the left. Here we're approaching 3 from the right. You can see that the value at 3 is undefined, but you can also see that it's approaching 0.125. So from the left, it's approaching 0.125. From the right, it's approaching 0.125. So therefore, even though it's undefined at 3, my limit as I approach 3 is 0.125. So that tells me that this probably was something that factored in the denominator, and my x minus 3's canceled, and that is a hole. Remember, when there's a hole, that's a removable discontinuity, and as long as it's removable and not jump, you are going to have a hole there, and you're going to have a limit that exists. So if I do the minus 3 here, and on this one, it's going to be the plus 5. So these x minus 3's cancel. And so really this is going to look like 1 over x plus 5. And that's why there's a hole at x equals 3. That's why that limit exists. All right, so by evaluating certain types of functions at a particular value, we may not necessarily have a sufficient understanding of the function's behavior at a specific point. This is especially true for rational functions that contain discontinuities. This is why the idea of a limit is so important. Rather than just going directly to some x value using direct substitution, we can approach a point from either side to get some sense of behavior in the neighborhood. So look at the photo of the arch support construction for the Hoover Dam Bypass Bridge 2009. We can tell where the missing section is going to be. The actual height at that point would be the limit. With limits, we can discuss behavior at a point, whether the point exists or not. With limits, we are looking at the y value of the graph. At the y value the graph approaches, not the actual y value at that point. So this actually is like having an open circle there, where it's approaching it, that value from the left and approaching it from the right. So when finding limits, ask yourself, what is happening to y as x gets close to a certain number? You are finding the y value for which the function is approaching as x approaches c. So here's our limit existence theorem. The limit as x approaches c of f of x exists if and only if the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x equals some real number L, right? Equals L, where L is a real number. So verbally, the limit as x approaches c on f of x will exist if and only if the limit as x approaches c from the left is equal to the limit as x approaches c from the right. And so that's super, super, super important. Example number 6, you own it. In the box below, complete the sentence in your own words. So in order for the general limit to exist, the function, and please pause the video right now and try to write in your own words what that means. Because remember, this is your general limit, right? That's your general limit there. And so it exists. In order for the general limit to exist, the function, and hopefully you are able to write something down on your own. When you come back, we're going to say something like the function must approach the same y value from the left-hand side and the right-hand side. In order for the general limit to exist. However, the function value may or may not be defined here, which I think that is probably the hardest thing for kids to grasp, is that, you might have, there might be an f of 3, or, that equals some value, or f of 3 might be undefined. And, either one of these situations can still have a limit, a general limit that exists, depending on what else the function is doing. All right, example number 7, sketch a graph to satisfy each set of conditions. F of A is undefined. X equals A is a point discontinuity. And the limit as x approaches A of f of x exists. So they want us to, sketch a graph. Let's just say, okay, here's my A. F of A is undefined. Okay, so, oops. Let's say there's an open circle there, okay? X equals A is a point discontinuity, okay? So that means that, that's an open circle. The limit exists, though. So that means that, this could have been going like that, and maybe like that. Or, yeah, it could even be a straight line. And you could have drawn anything, but it couldn't have a jump discontinuity. Okay, it's a point discontinuity, so that's a removable discontinuity. That's a hole. So it had to, go like this, have a hole, but then continue on from that hole. All right, the next one, the limit as x approaches A of f of x does not exist. X equals A is a jump discontinuity. So if we put our A right here, and f of A is defined, there's all kinds of different ways that you could draw this. You could make it so that because oops, it keeps taking it and making other things, doesn't it? It doesn't want me to draw a parabola. It could go like that with this going like that. But it has to have a jump discontinuity, and the limit can't exist, so that means the limit from the left does not equal the limit from the right. You could also have had something like, if this is your A, you could have had an open circle here, open circle here, and nothing else, undefined for A. Oh no, it said it had to be defined. So you could have had it defined here, like that. So it could have looked like that. Remember on this one, I forgot, I wanted to show you that this exists. The limit as x approaches A exists because, oops, sorry. Because look, if I'm approaching from the left, my values are approaching this f of A, and if I'm approaching from the right, I'm also approaching f of A. So that means since the left-hand limit equals the right-hand limit, even though it's not defined there, it would have a limit. Okay, that's the